So, this is a continuation of the previous lecture, and here we are going to just see the digital PI control implementation and Verilog HDL based implementation. In fact, we have already learned digital PID controller. So, PI controller will be much simpler. So, in this lecture we are first going to talk about the mixed signal current mode control and digital PI controller. So, this architecture has been we have discussed multiple times, and then we have also discussed in the previous two lectures regarding what are we going to do, which part in digital and which part is analog. So, this red curve which is indicating it, these are all digital data, and what we are going to do, we are in FPGA we want to implement in the Verilog module, we want to create this mixed signal current mode control block, which we have also discussed. Then we have also discussed that the main module which consists of this interface input and output, scalar as well as vector input and vector output, scalar output also. And we have also discussed that what are the parameter that we are taking. In fact, the PID controller is not needed. So, we can remove this, we are just using the PI controller because it is current mode control. This we have discussed that we are capturing the output voltage and we are instantiating clock generator digital PI control current reference PWM. So, we have explained this in the previous lecture, we have explained this earlier in the context of digital voltage mode control. Now, we just want to highlight digital PI controller, which in the generic form of PID controller is also discussed. So, PI controller, if you look at it, can be we want to update the PI controller with respect to a clock, which can be a switching frequency clock or any other clock. Here we are not talking about event based PI controller, but we can also implement event based PI controller, which we did the MATLAB simulation. So, here we need a proportional gain and the integral gain, and this is all in discrete domain. This is all in discrete, or I would say digital domain. I would say this is in digital domain. That means there will be number, digital domain, and this will be simply number, and this we need to know the Q format, which we have also discussed. Okay. So, if we see, that means this will be overall integral control, this block plus your, this is a proportional control, this is a integral control. The integral control has two parts, the history term plus the instantaneous this gain factor. Okay. So, that means we need to talk about Q format, and for the error signal that we will be talking about, it is Q1.9 and which we call it as a NE, because it is a digital number. Okay. And Kp, if we go back to the previous thing, that Kp we are taking 4.6 format, Ki 1.9. That means we are talking about Kp Q 4.6 and Ki Q 1.9. So, when you multiply Kp into V NE, then we have discussed it will be 5.15, but we can resize to Q 4.15 by dropping 1 MSB, this is sign bit. Then we also know Kp, so this I think better I should write NE. So, NE into Pi Ki. So, this will be in which format? Q 2.18 and which can be scaled to 2.1.18 by dropping 1 MSB. So, this is what the module name digital PI controller. Here we need a switching frequency clock, because we need to compute the integral with respect to the clock synchronism. Error signal it is taking, then controller output, then Kp Ki, and input as a sign NER Kp Ki, though they are all 10 bit sign, but they have a different format. So, what is NER? This is Q 1.9. What is Kp? This is Q 4.6 and this is Q 1.9, and then input, this is a scalar signal. Output, what is the NCON format that we are going to discuss. So, first the proportional temporary, it is 9. So, that means it is, we are talking about 5.15, 20 bit. Integral, so this is the proportional case. Integral, it is 2.18. Why it is coming? Because what is n, I mean we will discuss about this, and then after resizing this will be q 4.15, and we will discuss about this q 1.18. And we are setting an upper limit, because integral saturation is one of the major problem, and we want to make sure that integral, if it goes below 0 and all 1, then it will become negative. That means integral, suppose the maximum value, if you further increase, there can be a wrapping error and it can go all the way down, because it is a 2's complement number. So, you have to be very careful. So, we are setting a limit of the integral, that means if the integral value output goes some higher, then it will simply hold there. Okay. So, now this Kp, you see this is q 4.6, this is q 1.9. So, naturally this will be q 5.15, and after resizing this is coming to be, so after resizing, so here we are dropping one NSB, it is q 4.15. Integral, this will be q 2.18, after resizing it is coming q 1.18. Now, inside the integral you have that one history term. So, here this is the history term, it is like u n minus 1, this corresponds, and this corresponds to like this corresponds to what? So, this particular term is coming from here, which is a resizing of k I. So, it is linked with k I into V error n, right, and this is nothing but your u I n, but we need certain resizing, and here it is like u n minus 1 is equal to u I n. So, the typical standard, but this is just a representation, we need resizing, and then this is the resizing is happening. So, the instantaneous value, since we have n this one, this was q 1.18, but the proportional that we got for the proportional term, that means n proportional, we got q 4.15. So, we need to take this into this format. So, we need to match this format. So, we need to convert this q 4.15 to match this. So, for this bit we can simply discard 3 bits, and this is what we are discarding, 3 LSB we are discarding, and another 3 MSB we can do sign extension, and this is what we are doing. So, we are manually extending 3 times, but it can be done in 3 times that n initial temp 4, but somehow this was not working. So, we just make it 3 times repeatedly. So, this is your instantaneous value, and this now become q 4.15. Okay? But this is not the end of the story, because we still have to consider the saturation limit. That is why it is going inside and is checking whether this instantaneous value is greater than max, then it will be set to max, or it will pass the current value. So, now this one is the integral. So, this corresponds to u I n, and this corresponds to u p n. So, this is your u I n, and this is your now u of n, that is your control output, which we typically consider. So, this is the one which is this one, and this is the one which is this one, and this integral term, this is the one which is, or maybe we will use a different color, we will use this term is here. Okay. So, in summary, we have discussed Verilog HDL programming of mixed signal peak current mode control. We have discussed Verilog HDL programming of digital PI controller. So, in the next lecture we want to show some experimental results of this mixed signal current mode control. That is it for today. Thank you very much.